Let's go ahead and get started. Right for class, someone asked a very good question. I want to bring it up. If you go to the registrar's website and you get the final exam schedule, it's listed by the day and time your class meets. Okay, not that. This, right? Or maybe not. I don't know what this is. All right, where's it at? Oh, here it is. Well, that's fall, spring. It'll look like this. I don't know where it's at now, but where's the? Well, apparently, okay. So if you go by the day and time your class meets, you'll go to the wrong place. Basically, I'm sorry, I gotta use this one here as an example. If you go by the day and time your class meets, you'll go to the wrong place. What happens is there's block scheduling. All calculus students take the exam at the same time. This is an example. I'm sorry, I don't know where the exact page is for fall, but all calculus exams take place on the same day and the same time. So I don't know where that is for this guy though. I guess when they switched to rooms, when they switched this thing to be room roster, they actually went through and put every room. Anyway, I guess if you read that might actually tell you the right place. You might want to. Anyway, I don't want you to be confused. Like other classes, they just say, oh, just check the registrar's website. But calculus and some other classes that have block scheduling, you can't just check the registrar's website. You'll end up going to the wrong place. Okay, so let's stick to what we have. It's the correct time. It's the correct date. And I even gave you a place last time we had class. I said it's going to be in Chem 102. It is the lecture hall that is in the Chem building across from Irvine, gigantic lecture hall. And the purpose we're in there so that we can spread out and have every other seat. Not every other row, but at least every other seat. And it's going to be 9 to 11 a.m. on Tuesday the 18th. Have to be there that time, basically. So no confusion. Everyone's clear? Okay, good. I've been recording videos of the lectures, and you can get to them through here. Not all of them are there. Some recordings didn't work. I put up a final homework assignment. Call it homework number 9. Over material that's a wrong date. I was going so fast this morning I forgot to change this date. On the thing it says when it's due. It's the 7th. Friday the 7th is due. This material is on the exam, and this thing isn't due until after the exam. But to practice for the exam, you should do this assignment. It's 8 questions. There's an online assignment too, with material that's on the exam. That's the correct date. That is due the 9th. This thing is due the 7th, Friday the 7th. This is due Sunday the 9th. And so that's updated. The exams page, also updated. It has the much anticipated, a lot of students ask me about, I want some book problems to try. Oh, there's a ton. If that's not enough, do the evens. And a practice exam. This is the actual 3rd exam I gave. I think it was last spring or fall. Let's see. Fall. The 3rd exam I gave. The full exam. So I'll let you chew on it for a little while before I give you the answers. What's the exam going to be on? Everything since last exam. Technically 7.1, but really what that is just everything we've been doing now with exponentials and logs. So it's not a new section. What we've yet to cover is 5.5 and 5.6, and we've yet to finish 5.4. So we're going to do that today and on Friday. So with that reason, we had to push the exam to be Wednesday. I buried the lead. Sorry, that should have been the lead. The rules are the same. I just didn't want to put them on everyone, so I moved it down here. What I'm going to be working on is getting the other professors' exams to study for the final, you need to know what the other professors are asking on their exams because they're making up part of the final. We're each going to give a third of the final. And so on this page, I'll have Professor Tausner first exam, Professor Wong's first exam, and their second and their third once I get them. So that'll be practice for the final. But for us, you have enough here to practice for your third exam. And eventually, I'll make all these pages have a link to the solution videos. I guess this page doesn't link to there, sorry. But the homework page links to the lecture videos, and the notes page should link to the lecture videos. Okay, good. All right, let's go ahead and get started. That's enough preliminary stuff. What did we do last time? We talked about the fundamental theorem of calculus. We did more examples of why we care about finding the antiderivative. Because we don't want to do the approximate by finding rectangle way. We don't want to do the limit definition to find the area. So this is the best option. It's using the antiderivative. We did a bunch of examples last time. We ended with this one. So we'll pick up from there, doing two more, and then we have to talk about this other part to the fundamental theorem of calculus, and if we have time, we'll start u-substitution. So we're going to do these two problems, but let me... we're going to work them out together. They're already worked out on the slides. I just want to work them out together. E to the x from 0 to 1, e to the x from log 7 to log 4. Okay, so okay, the graph of e to the x looks like this. We're worried about from 0 to 1. So the picture of the area that we're trying to find is this area here. On one exam, I gave the students the question as a picture. They'd have to interpret it as, oh, I'm trying to find area, and they have to write the symbol, and then they had to do it. Okay? But it's the same thing. You're trying to find the antiderivative. You ask the question, what function has that integrand, the thing that's inside the integral is called the integrand. What function has e to the x as its derivative? Once you answer that question, you've got in your hands the antiderivative. Okay, and with e to the x, it's just e to the x. We'll see how to handle when it gets more difficult, but for right now, we're keeping it simple. No need for a substitution or anything like that. We won't be able to integrate e to 5x right now. We have to wait till u-substitution for that. But anyway, we have it. So what do we do with this antiderivative? Fundamental theorem of calculus says that we can just take that antiderivative, call it capital F of x, evaluate at the upper limit of integration, evaluate at the lower limit of integration, and subtract these two, and that's the answer to the question. That's the exact area under the curve. E to the 1 is e. E to the 0 is 1. Subtract these. The answer to the question is e minus 1. It represents the area under that curve. E is a number like 2.71 and some other things like pi. It goes on forever, never terminates, and it doesn't repeat. And so that's the answer, e minus 1. That represents that shaded area. To make it more interesting, let's change the limits of integration to be the log of 4 and the log of 7. Okay, this is the stuff that's like in 7.1. Things that we do for chapter 5, but now apply to e's and logs. Antiderivative is still the same, e to the x. But we have to plug in a log 7 and a log 4. What is e to the log 7? They cancel and you just get 7. E to the log 4 is a 4. The answer is 3. Okay? They'll be more complicated than this, but this is just to get us started. This is our first experience with having e inside of an integral. Questions on that? Okay, now with log involved, it's 1 over x. So 1 over x from 3 to 4, 1 over x from root e to e to the 4. Okay. One over x from 3 to 4. Remember, you can't use a power rule in reverse if the exponent is a negative 1. In the same token, though, if you have 1 over x squared, you can't use logs. So I get students mixing both of those up. I get students that want to use the power rule in reverse on this one. I get students that want to use log on this one. Don't do it. Okay, the antiderivative of 1 over x is log x. Only 1 over x. The antiderivative of 1 over x squared is not log x squared. Don't do that. And when I say log, I mean natural log. Okay, so we found the antiderivative. Capital F of x, we call it, is log of x. We need to plug in a 4. We need to plug in a 3 and subtract. So the answer to this question would be log of 4 minus log of 3. And then you look at the answer key or the solutions, the multiple choice, and you're upset. You know you've done it right, but your answer isn't there. They've added an extra step. They rely on your log property skills. When you have log of A minus log of B, you can combine them into one log as division. So when you look at the answers, the one that they'll be looking for is the log of 4/3. And it could be more complicated. It could be numbers out front, which then you have to bring those numbers up as exponents. Use other properties of logs. Okay. And then the limits of integration can be strange. Keep the integrand the same. Let me just say this here. I said it. Let me write it. The antiderivative of 1 over x squared is not natural log of x squared. Don't do that. All right. So the limits of integration could be exponential. Root e and e to the 4th. Antiderivative is still log x. But now you'll be plugging in an e to the 4 and plugging in a root e. You look at the back and you look at the multiple choice answers and you get upset. And you have to spend time in algebra class putting logs together. What should you do to the first thing? That's natural log of e to the 4. What is that? It's 4. Either you cancel or you bring the 4 down and realize that log e is 1. This is a 4. Do the same thing with the root e, but get rid of the radical symbol and make it a half exponent. In disguise, that's a half. And the answer is 4, take away a half. Okay? Be able to do that. And it does get more complicated. All right, great. That's enough of antiderivative fundamental theorem of calculus. Now let's move on to actually, it's called the first part of fundamental theorem of calculus. It won't be our focus. Our focus is on that second part. It's the one we're going to use more often. Here's what the first part says. It's the less useful one, but for some reason it's called the first part. So I have this function f, and it's continuous. And I'm going to make a new function g. The function g is going to be a function that will accumulate area. Okay? Here's the picture. The function g, when you plug a number into g, what you'll be doing is that will be your upper limit for your area under the graph of f. The t is just called a dummy variable. It's like I can't put x's. I want to put x's in there, but I got x's in my limits of integration, so I just changed the variable to something else, and the normal thing that you change it to is a t. So we have this area accumulating function. G of x will accumulate area under f of x from a to x. Okay? So when x is close to a, g is small. When x is further away, as long as this thing stays above the axis like this g of x will be an increasing function. Something strange happens when f dips below, then you start getting negative area, so it starts taking away, it becomes a decreasing function. Okay? Alright, but we haven't said anything. This is a function, and the fundamental theorem of calculus part 1 says the following. It says that with this special function, the derivative of it is the f of x. The derivative of an integral is the thing that's on the inside. It shows how the two operations cancel each other out. I might have to erase what I have here because the next animation is going to be over that. Yeah. The function is continuous, and it's differentiable, and we know its derivative. Can I just move that? Oh, I'm sorry. Let me keep it. I want to keep that statement, but I got to move it. Can I just move the whole thing? All right. Don't worry about what the arrow's doing, but the point is how we use that thing. So this g of x accumulates area underneath the f function. It's a continuous function, and you can take the derivative. Even more than that, we know what the derivative is. The derivative is the function that's on the inside. When you take the derivative of an integral, they cancel each other out. In symbols, it's taking the derivative. The symbol of take the derivative of what's after is called d over dx. If you take the derivative of an integral, the point is that what happens is these two operations essentially cancel each other out and replace the dummy variable t with the variable that's in the upper limit x. It's equal to f of x. Okay. No matter how complicated the formula is, it's a simple replacement. Whatever the t's are, I put x's in there and I'm done. Okay. So no matter how complicated the function is, if I want this guy's derivative, all I do is rip out the integrand, take the t's out, and put x's in. That's it. The derivative of g is the root of 3x minus x squared. The derivative, these guys cancel each other out, and you get the root of 3x minus x squared. Okay, the a has to be a number though. Okay, has to be some number, a. Okay, and the upper limit can be the function x. It can be even more than the function x, and we have to see what to do with that. But it has to be in that order that the upper is the x and the lower is a number, any number. Doesn't really matter as long as the function is continuous on that number. Any questions about that? Pretty straightforward. Here's a question. Yes.
So in this case, it works, but then if x is a number, would you be able to cancel that out too?
No, only do this if you have an x.
Okay.
If x is a number, then you're talking about an area under the curve. It's not this g of x function anymore. Oh. This time what's different is the x is on the bottom and the number's on the top. How do you remedy it when it's backwards? You flip it and you put a negative out front. You make it the way you want it to go, and you put a negative out front. And then you take the derivative. It only works when it's in that order. Number in the lower limit, x in the upper limit. So that negative will then be carried on to the derivative. And the derivative of this function is going to be negative cosine squared on 4x. Question, yes?
So why do we change from t to x?
I can't have x's inside and x's in there. I can't have both have x's. So t is called a dummy variable. T is anything you want to be. Sometimes it's a u, sometimes it's a w. Whatever it is, it's a dummy variable just to hold the spot because x is coming to replace it. It gets more complicated. It might be more than just an x. It might be a function. What do we do with something derivative-wise when it's more than just an x? I heard it.
Chain rule.
Chain rule. Very good. That's it. Do the same thing, but be careful. When you replace the t's, you're not replacing them with x's. You're replacing them with the entire function. And then chain rule. You can't forget that. Multiplied by the derivative of 3x squared. Okay? Which is 6x. And just leave it like that. I mean, you can simplify it if you want. I mean, that's it, though. That's the derivative. It could be, I give you one of these and I tell you to evaluate the derivative somewhere. So you just be plugging into this, a particular value of x. Okay. The why it works is because there's a substitution kind of. If I let u replace the x squared, then I could do it. But the problem is that I now have the derivative of something that doesn't have x's in it. And so I have to put on the derivative of u with respect to x to get it to work out. You don't have to write this down, but this explains why that extra step is there. Go back and replace the u's with the x's. Okay. So this is an explanation as to why this is happening. The u holds the place, but when you do the substitution, you're going to have to remember to take the derivative of u, and that 6x part gets multiplied on the end. But you don't have to write it down, I just want you to see it. So just remember to do it. If you recognize that function, which should just be an x, is more than an x, then remember the chain rule. But don't forget, though, when you're plugging in, you're not just replacing t with x, you're replacing t with that whole function that's up there as the upper limit. And you can simplify it if you want. Don't worry about it. All right, so what's new with this one? What's new with this one is that there is no number as the lower limit. or the upper limit. There's no numbers involved at all. So what do? We pick a number, any number, as long as the function is continuous at that number. With this particular function, there's nothing that you should need to worry about. T squared plus 1 is never 0. So you get to pick any number you want. Okay? And in general, root x is going to be smaller than tan x. So they are kind of in the right order. You don't have to worry about flipping them. So we do the following. We pick a number, any number, and we say we go from root x to that number, and then we go from that number to tan x. So the number I chose is 1. The number means nothing to us. We never even used the number in the other examples. We're not going to use the number here. It's just necessary to have it so we can use the fundamental theorem of calculus. I don't know, maybe 1's not a good choice. What's the tan of 1? One radian? I guess it's more than yeah. I think we're good. I think it's less than. I think it's more than 1. We're good. 1 is good. So what do? One of them's backwards. One of them's going the right way. The one that's backwards, flip it. Put a negative on there. Yes?
How do you not need to flip root of x in your original?
Yeah. Good question. You're kind of restricted as to which x's you can actually use. Like you can't use, pi over 2 or anything like that, or negative pi over 2. But if you think of just the first fundamental period of tan, in fact, you can't even use negative x's. So you're really only restricted to only think about x's between 0 and pi over 2. And for those x's, we're going to say that the root of that x is less than the tan of that x. It's not something you have to worry about. So take the derivative. Replace the t with the function. But don't forget, that's more than just an x, so you're going to need a chain rule. Replace t with root x. Replace t with tan x. There's a plus sign between them, yes. But you have to multiply by the derivative of root x. And the derivative of tan x. We can simplify that. It actually turns out to simplify pretty nicely because of the identity. 1 plus tan squared is secant squared. Root x squared is an x. This root x up here and that root x down there cancel. So when there's a chance to get better, simplifying wise, we'll do it. Do all that cancellation and we get that. Don't forget the negative is there. This 2 comes and goes here, but it's times the quantity of x plus 1. And this tan x survives. Questions on that? Yes?
On the third line, how did you know to flip the root x's?
How did I know to flip this? You need x at the top. Wow, this is weird. Okay, this is from some midterm somewhere. I don't think it's a final exam. This is this area accumulating function in action, where we don't actually have a formula for this function f. We have a graph of it, and we're going to accumulate area. What is g of 14? Replace the x with a 14. G of 14 is the integral from 0 to 14 of this f function. It is the area under the graph of f between 0 and 14. Okay, but we don't have a formula for it. We can't actually do the antiderivative. It's like what we did last class. We have to recognize familiar shapes and break it into parts and just add up the area of all those familiar shapes. Remembering, though, that when we have special properties like the fact that if you ever dip below the x-axis in your graph, then your area is actually negative. Okay? The placement of these dots are supposed to signify the center of these semicircles. And so it's centered at 3. It has a radius of 3. Okay? So pi r squared is the area of the whole circle. You only have half of it. So 9 of those, 9 pi, but then divided by 2. That's the area of that semicircle. What's the area of the rectangle underneath that? Length times height. It's 2 tall. It's 6 wide. It's 12. What about the triangle next to it? 2. Why? Because it's 1/2 the base times the height. It's a right triangle, so half of 4 is 2. Great. Now, as soon as it starts to dip below, alarm should go off. When you find these areas, they are no longer positive. So it's covered the actual tick mark. Sorry, this is a 9, this is a 10, this is 11, 12, this is 13, and this is 14. So that's just another 2 by 2, half of that. But we recognize it as a negative 2 instead, though. What's the area of the rectangle? What's the base and the height? 4 and 2. This distance here is 4. This distance here is 2. But it's -8, not 8. What about the semicircle down there? What's the radius of it? 2? Okay, so if it was a full circle, it'd be 4 pi. You only got half of a circle, so it's 2 pi. But it's -2 pi. Add all that up. You got the total area under the curve. Stuff that looks alike, combine them together. Numbers with numbers, parts of pi with parts of pi. Four plus 5 pi over 2. Very good. So this is the function in action, combined with the properties that we learned from last class, combined with the strange functions that make up familiar shapes from last class. What if you stop at 10? We don't do the stuff that's after 10. Take all the stuff that goes up to 10. That's all. So you don't get the rest of that. You don't get that rectangle. You don't get that semicircle that represent 10 to 14. You don't get those. So you just get an answer. All right, here's a tricky question. I like the derivative at 6. The derivative not of f, the derivative of g. G prime at 6. What does it mean? Well, first, what is g prime of x? F of x. Very good. So if I want to plug a 6 in, I just take f of 6. If I'm looking at a graph, how do I get f of 6? What does that mean, f of 6? When x is 6, it's the y value. So that's why the answer is 2. And finally, absolute minimum value of the function. Absolute minimum value of the function. This goes back to chapter 4, earlier in chapter 4. Absolute minimum value of a function either occurs at the endpoints or at any critical point in between. So let's go get the endpoints. If you plug in 0, you're talking about the area from 0 to 0. That was one of the properties from last class. You don't get any area when you have the upper and lower limit the same thing. Okay, so if we're doing this chart, right, we have 0, which gave us 0. We have 14, which gave us 4 plus 5 pi over 2. We need critical numbers in between. Critical places where the derivative is 0 or undefined. What's a place where your derivative is 0? I need g prime to be equal to 0, but what's g prime? G prime is f. So if I want to know where g prime is 0, I got to know where f is 0. Where's f 0? The y value is 0 at 8. So that's a critical point in between x equals 8. And when you get that, that's not right, is it? You don't get this minus 2 on here, right? You just get this part. Yeah, this whatever this is saying is wrong. The answer is 14 plus 9 pi over 2. I don't know. Yeah. Say what?
You do. Yeah, you treat it.
Oh, where's 8 at? That's 10.
10, yes. Yeah.
I don't need that. I don't need that. I don't need that. This is where it's 0 at. I don't need this part. The function is 0 here. I only go up to here.
But it's G of 10.
I don't need G of 10. G of 10 is this answer. Yeah. I'm not looking for G of 10. I'm looking for G of 8.
Oh, yeah, I thought you were talking about.
But this answer is right. I'm talking about another answer over here. This jump down here is wrong.
I got it.
What's the biggest of these values? Hopefully it's obvious that this guy is the biggest. So that's your absolute maximum value. I'll rewrite the slides to keep that on there, and I'll get rid of that wrong information there. Minimum? Let's change the question. Maximum. There we go. Oh, it's from a fall 2009 exam, I guess. It's from an exam. All right, let's get a start. Let's not end class early. Let's get a start on u-substitution. And I'll put up some skeleton notes for next time for this last section, 5.6. Let me just give you the background. We won't get a chance to do any problems, I don't think. So let me tell you what u-substitution is. Basically, it's the chain rule in reverse. I don't know if it ever says that on these slides, but in essence, that's the big picture. U-substitution is the reverse chain rule. If we got a reverse power rule, we could probably have a reverse chain rule. And there it is. It's called U-substitution. Okay? There's a reverse product rule, but you got to wait till 104 for that. It's called integration by parts. Here's what it says. Basically, you have some function that's an inside function and some function that's an outside function. You have to identify who's who, basically. And what you do is you let u be the inside function, and you take its derivative, and what needs to be true is that this outside function is the derivative of the inside function. Okay? And here's how you execute it, basically. By letting u be equal to g of x, its derivative, but you do it as a differential, is g prime of x dx. So it's like a substitution, a replacement. G prime of x dx gets replaced by du. G of x gets replaced by u. This integral, now the whole point is, it's supposed to get better. Right? If it doesn't get better, then you're not doing it right. Okay? And the point is that when you're all said and done, you end up with fu. Du. Okay? And that's supposed to be better. That's supposed to be like the old integrals that we've been doing. Okay? Let's see one. We might have time for one. My inside function is 1 plus x cubed. It's underneath a root. It's inside the root. My outside function is x squared. Okay, it's not exactly true that the derivative of the inside is exactly the outside, but that's okay. It's up to a constant. It is the derivative. So what do? You let u be the inside function. Let u be 1 plus x cubed. Take the derivative, but do it as a differential. What's the derivative? It's not x squared. It's actually 3x squared. 3x squared dx. So now it's all substitution. You want to replace this guy with u. But the other part is also necessary to be replaced. It's not 3x squared dx, it's x squared dx. So what do? Get rid of the 3. Divide both sides by 3. So now you know how to replace x squared dx. You replace it with 1/3 of du. There's an extra factor of 1/3 that you have to incorporate. Okay? Let me not do it the way it's done here. So what happens? This guy becomes the root of u. These two guys together become 1/3 of du. Okay? Let's integrate that. It's better. This fu is better. Constants, they can come outside. This u radical symbol does us no good. Let's make it 1/2. What is the antiderivative of u to the half? Power rule in reverse. You add 1 to it, and you divide by the same thing. Dividing by 3/2 is times by 2/3. This 1/3 gets carried along for the right. In essence, you did all this to find that 2/9 of u to the 3/2 is the antiderivative. Go back. Your job was to find the antiderivative. You took this little detour, but you have it. 2/9 of 1 plus x cubed to the 3/2 power is your antiderivative. Now go plug in the limits of integration. We don't have time for that. We'll do that next time. See it. I didn't bring the attendance sheets. Sorry. How you been, man? You right? Where you been? You been here, man?
I've been
You been there? You're not sitting there.
I don't sit there. Next
Yeah?
to Sierra. Yeah.
Yeah?
Yeah, but yeah. But
Okay.
anyways, I was doing my schedule for next year.
Yeah, what's up
and
with
the
that?
only one that I can fit in is the 104 at night. And I said I need a permit for that.
Yeah, they don't give you a permit until the first day of classes.
Okay.
It's crazy. So you gotta wait till the first day of class. They'll give you the permit. You gotta go in basically thinking that you're gonna get it. I mean, you might not get it, you know. So
Should I sign up for like a different. You think I should sign up for like a different one, like just in case? Okay.
As like a fallback. You don't want to get left without being able to get in. You know.
Okay.
So was it the 104?
104 is like the evening class.
If that doesn't work out, there's another plan. I teach it in the summer.
Oh, so you, okay.
Online.
Okay.
So that's another plan. So if all fails, definitely try this thing first.
Okay.
If it works, it's great. If it fails, there's a plan B.
Okay.
It requires you to take a summer class, but it's summer one. It's online. You can be wherever you want to be.
Okay.
It's possible.
All right.
Okay.
Thank you.
All right. Take it easy. That's it. I think that's what Andrew's going to do.
Okay.
Andrew Lisa.
Yeah, that's what he was saying. He was trying to get the evening class.
Yeah. Hopefully, I'm the one teaching it. I put a strong please let me teach it beg in. I don't know what's going to happen though.
Okay.
Okay. Yeah.